Today we are going to study an important concept in quantum mechanics, the uncertainty relation. Uncertainty relation. To do so, let us introduce an operator delta A corresponding to an operator A. Delta A is of A minus expectation value of that operator. Now, the expectation value of the square of delta A is called the dispersion. That means delta square and its expectation value is equal to the expectation value of A minus expectation value of A its square. If we simplify this, we will get A square expectation minus 2 expectation of A into expectation of A minus plus square of expectation of A, and this means A square minus 2 expectation of A is its square plus expectation of A its square. This equal to A square expectation minus expectation of A its square. This is nothing but the variance or sometimes it is called the mean square deviation. Now we'll ask a question, that is, what will be the value of dispersion when the state is eigengate of the operator A. Let us see that. Suppose that A is a normalized eigengate of A corresponding to eigenvalue A, then A expectation value of A operator will be equal to this, equal to A since A is a eigengate of the operator A, that means AA equal to AA, which is A, which is nothing but A. Now, what is the expectation value of the A square in this eigengates? That will be A and A operator on these eigengates. That will be A. That is nothing but A, which is A square. Now what is the dispersion? Dispersion means delta a square, its expectation will be a square expectation minus x a expectation of a its square. That means a square minus a its square, that is 0. That means the dispersion is 0 when the state is an eigengate of the observable A. Roughly speaking, dispersion characterize the fuzziness of an observation corresponding to an observable. For example, suppose that the state is an eigengate of Sz. Suppose the eigengate is plus Sz. Now if we ask what is the value of dispersion corresponding to the observable is x in the same state. Let us calculate that. What will be the expectation value of Sx? Sx will be plus Sx plus, as we know that Sz plus Sz can be rewritten in terms of eigengates of Sx as follows: 1 by root 2 plus Sx plus minus Sx. Then if we operate this state with Sx, what will get? Sx plus Sz 1 by root 2 plus h cut by 2. If we operate Sx with in this state, we will get plus h cut by 2 and the system remain in the same state since it is eigengates of Sx, minus if we operate Sx in this state, we will get minus h cut by 2 and the state remain in the same state Sx. That means 1 by root 2 into plus Sx minus Sx to h cut by 2. This is nothing but the Sz, the state of minus Sz, that is, this is nothing but h cut by 2 into minus Sz. That means the expectation value Sx will be plus Sz Sx plus Sz that will be h cut by 2 plus sz minus sz. Since these two eigengates are mutually orthogonal, that means it will be 0. Now let us calculate what is the expectation value of sx square. That will be sz sx square plus, as we calculated previously, we know that sx plus sz is nothing but h cut by 2 minus sz. Now if we again operate in this state with sx, we will get sx square plus sz, that will be h cut by 2 sx into 1 by root 2 into, if we write these eigengates in terms of eigengates of sx operator, we can write it as 1 by root 2 plus sx minus sx. So h cut by 2 into 1 by root 2. Again it will give h cut by 2. The state will remain in the same state, and that will be minus h cut by 2. That will be the plus h cut by 2, and the system will remain in the same state sx. That means we'll get h cut square by 4 into plus sz. Now what is the expectation value of sx square? That will be plus sz sx square plus sz. That will be h cut square by 4 into plus sz plus sz, which is equal to h cut square by 4. Now what is the dispersion? Dispersion will be delta sx square, its average, its expectation, equal to expectation of x square minus expectation of sx its square, that is h cut square by 4 minus 0, which is h cut square by 4. Now we know that there will be a fuzziness if we want to measure the sx if the state is in the eigenstate of the operator sz. When the state is an eigengate of sz, there will be some uncertainty, there will be some fuzziness when we want to measure sx. That is represented by this dispersion observable. We can also call this dispersion as observable. As we said in previous lecture, that when we consequently measure two observable, when these two observable are incompatible, then there will be an uncertainty. That is, if A and B are incompatible, then there will be uncertainty if we consecutively measure A and then if we measure B. Why it is happening? Because why it is happening? Because the operator B interact with the information that is measured by the operator A. Now we will characterize this uncertainty by a relation. which is famous in quantum mechanics, and it is called the uncertainty relation. That is, the dispersion corresponding to A, which is this, and the dispersion corresponding to the operator B, which is this, is should be greater than equal to 1 by 4 into square of the expectation value of A comma B, its commutation. This is nothing but the fuzziness or uncertainty corresponding to the observable A into the uncertainty corresponding to the observable B, its multiplication should greater than equal to 1 by 4 into this quantity. Now we are going to prove this relation, but to prove this relation we have to use three lemma. Now we will state that lemma and prove that, then we will going to prove this relation. First, the famous Schwarz inequality. The Schwarz inequality is similar to the vector product inequality in the 3D vector space, which is A dot B its square equal to mod A square mod B square into cos square theta. Since cos square theta is less than equal to 1, that means this will be less than equal to mod A square into mod B square. This mod A mod B is nothing but A dot B its square is should less than equal to A dot A B dot B dot B. So in vector space, complex vector space, this relation is simplified to that alpha, since in this vector space the inner product is similar to the dot product, that means alpha into beta should be greater than equal to mod of alpha beta square. Now we are going to prove this relation. So to prove this relation, let us first assume a state gamma which is equal to alpha plus lambda beta, where lambda is a complex number. As we know that gamma should be greater than equal to 0. That means alpha plus lambda star beta into alpha plus lambda beta should greater than equal to 0. That means alpha plus lambda alpha beta plus lambda star beta alpha lambda star beta should greater than equal to 0. Now this relation holds for any arbitrary value of lambda. Now let us take lambda equal to minus beta alpha by beta. If we put this lambda in this equation, we will get alpha plus beta alpha beta by beta. This is corresponding to this term plus minus alpha beta alpha by beta. This is corresponding to this term, and this minus beta alpha beta I beta greater than equal to 0. These two terms are similar, so that means this equal to alpha should greater than equal to alpha beta into beta alpha beta beta, which is nothing but alpha should greater than alpha into beta should greater than equal to mod of alpha beta its square. That means alpha into beta should greater than equal to mod of alpha beta its square, which is nothing but the Schwarz inequality. Schwarz inequality. Now, the second thing we require to prove the uncertain relation is the expectation value of a Hermitian operator is always real valued. So let us prove that. Suppose a Hermitian operator is A, its expectation value will be psi A psi. Any k vector can be represented by the normalized eigenkets of the operator A, as we proved earlier. That means psi can be written as summation of A dash C A dash, where A dash is the normalized eigenkets corresponding to the operator A. Now this is equal to, if we calculate the value of this, then we'll get A psi equal to A dash C A dash C A dash is nothing but a complex number, which is, if we operate psi A psi, that will be summation of A C A star A into A dash C A dash A prime summation of A prime. That is nothing but summation of A prime C A star A dash A prime. As we know, for Hermitian operator, the eigenkets are orthonormal. That means this is equal to delta A prime. That means A prime C A dash C A star C A dash delta A prime. That means this will be A C A star A into C A. This is a real number, since a complex number into its complex conjugate number, that means that is will be nothing but CA mod its square into A, and A is a real value. Why it is real value? Since it is a eigenvalue. It is an eigenvalue of Hermitian operator A. So the A should be real value. That means these total terms should be real value. That means the expectation value of A is always real value. Hence we prove that the expectation value of a Hermitian operator is always real valued. Now we'll see the third requirement for the uncertainty relation. That is lemma 3, which is the expectation of an anti-Hermitian operator is always imaginary. Anti-Hermitian means, suppose a dagger equal to minus a, then this operator a is called anti-Hermitian. Similar to the Hermitian operator, this anti-Hermitian operator has some property. Property number 1, that is all eigenvalue of a is imaginary. And the second is similar to the Hermitian operator, which is the all eigenk's are orthogonal other. So let us prove the first property. Suppose a is an eigenk of the operator a, that means a will be a. This is equation number 1. And the second thing is that a its dual correspondence, that is a dagger will be a star. As we know, a is an anti-Hermitian, that means this is equal to minus a will be a star. This is equation 2. A is not a null eigenkate. That means a plus a star should be 0. That means a star will be minus a. So this property only be seen for a pure imaginary number. So this imaginary number follows this property. So a is a pure imaginary number. So hence we prove that all eigenvalues corresponding to an anti-Hermitian operator is imaginary. Now we are going to prove the second property, which is all eigenk's are orthogonal to each other, by using the fact of equation 1 and equation 2. So let us prove that a equal to a and minus b equal to b star. Now if we multiply this equation by b and this equation by a, then add these two equations, we will get b equal to a b and minus b a equal to b star b that means a plus b star into b equal to 0. since B and A state are not linearly independent, that means A plus B star should, if A plus B star is not equal to 0, then B A equal to 0. That means these two eigenstate are orthogonal to each other. That means since we prove that all eigengates are orthogonal to each other. Now we can make this eigengate as well as normal also. Now we can write these eigengates as orthonormal eigengates, and since these eigengates are we can write this eigengate as orthonormal eigengates, then that means we know that any orthonormal gate vector, set of gate vectors, can be used as a base case of the gate vector space. That means these eigengates can also be used to span the whole eigenvector space. Now then let us prove the property, the lemma 3, that we need to prove the uncertain relation, that is the expectation of an anti-Hermitian operator is always imaginary. Let us prove that. So what is the expectation value of anti-Hermitian operator? Psi A psi. Then since we know that any gate vectors can be written in terms of in terms of eigengates of this anti-Hermitian operator, eigengate of anti-Hermitian operator A, that means A psi equal A CA A, that is summation of A CA A. Now psi A psi equal to A prime CA prime star A into summation of A CA A. That is summation of A prime CA prime CA prime star CA prime star into CA into A to A prime A prime CA prime star CA A delta A prime CA prime small square into A prime. And since it's a real number and it is a pure imaginary number, that means this total will be a imaginary number. That is, if suppose that a real number is lambda and a pure imaginary number is I lambda 1, that means the multiplication of a pure real number and pure imaginary number will be a pure imaginary number. So that means the sum will be a pure imaginary. That means the expectation value will be a pure imaginary. That means we prove that the third requirement, that is the expectation value of an anti-Hermitian operator is always imaginary. As we in a position to prove the uncertainty relation, let us prove that uncertainty relation, where we are going to use these three relations. Suppose that two incompatible operator is A and B. That means A comma B is not equal to 0. And let us assume that alpha equal to delta A in gamma, beta equal to delta B in gamma. That means then alpha into beta will greater than equal to mod of alpha beta square. I write this by using the Schwarz inequality. If we put these two values in this equation, we'll get gamma delta A dagger delta A gamma into beta delta B dagger delta B beta is greater than equal to gamma delta A dagger delta B gamma its square. Now since A is a Hermitian operator, its dagger will be delta A dagger will be delta. That means this will be gamma delta square gamma into beta delta B square. Sorry, this is gamma. This is gamma. That means gamma delta B square gamma should greater than equal to modulus of gamma delta A delta B gamma of the square. Now we can always write delta A delta B as half delta A delta B minus delta B delta A plus half delta A delta B plus delta B delta A, that is equal to half commutation of delta A comma delta B plus half delta A plus delta A comma delta B. Now let us see what is the value of delta A comma delta B. The commutation delta A comma delta B is nothing but A minus expectation of A comma B minus expectation of B. We simplify this, that means A minus A into B minus B minus of B minus B into A minus A. That means AB minus AB minus BA plus AB minus BA plus AB plus BA minus AB. That is AB BA minus AB minus BA, that is nothing but A comma B. The commutation relation of delta A comma delta B is same as the commutation relation of A comma B. Now let us check these two operators are Hermitian or anti-Hermitian. So first check the operator delta A comma delta B, its dagger will be delta A delta B minus delta B delta A, its dagger. That will be delta B dagger delta A dagger minus delta A dagger delta B dagger. Since these operators are Hermitian, that means delta B delta A minus delta A delta B, that means minus of delta A comma delta B. That means this operator is an anti-Hermitian operator. And let us check the delta A comma delta B, its adjoint will be delta B dagger delta A dagger plus delta A dagger delta B dagger. That means delta A delta B plus delta B delta A, that is delta A comma delta B. That means this operator is Hermitian, and this operator is anti-Hermitian, anti-Hermitian. That means the expectation value of delta A and delta B can be written as expectation value of half expectation value of delta A comma delta B plus half delta A comma delta B, where this is a pure real number and this is pure imaginary number. Pure imaginary number. That means this is equal to half some pure real number lambda mod, and this is equal to I into lambda 1. This is a real number, pure real number, and the whole is a pure imaginary number. That means delta A delta B, its mod square will be 1/4 lambda square plus 1/4 lambda 1 square. That means it will be 1/4 of delta A comma delta B, its mod square plus 1/4 of mod of expectation value of delta A comma delta B square. That means from this relation, we know that the expectation value of delta H square, the expectation value of delta B square should greater than equal to expectation value of A delta B, its mod square. Now what we get, if we write here delta A square delta B square should greater than equal to 1/4 of, since we know that the commutation relation of delta and delta B is equal to the commutation relation of A and B. That means 1/4 of expectation value of A comma B square plus 1/4 of A comma delta B square. Since these two are pure real positive number, since it is a pure real number and its square should be a pure real positive number, real positive number, that means delta A square its expectation, delta B square its expectation should be greater than equal to 1/4 A comma B square. If we write it clearly here, that means the dispersion of A, dispersion of B should greater than equal to 1/4 of expectation of commutation relation of A comma B its square. So hence we prove that uncertain relation corresponding to incompatible operator or observable, there will be an uncertainty corresponding to the observation of operator A of and operator B if we consecutively want to measure the observable corresponding operator A, observable A, a corresponding observable B, we will have some uncertainty barrier cannot cross in any experiment. So that is the spirit of this uncertainty relation, and this corresponding to the uncertainty when we want to measure an observable corresponding to operator A, and this is the uncertainty or the fuzziness corresponding to the operator B. So the multiplication of these two quantity should always be greater than equal to 1/4 of this quantity. So this is actually the uncertainty relation. Hence we prove the uncertainty relation. So thank you.